All right, let's work through this together now. I started it here. I initially made a mistake. I was trying to pick 3 random vectors in R3. And if you pick 3 vectors essentially at random, in all likelihood, they will be a linearly independent set. But I happened to pick a 3 there initially, and it was a linearly dependent set, so it didn't work. So I changed it to a 4. This is now, it turns out, a linearly independent set. By the definition of linear independence, that means this equation should only have the trivial solution. This is a homogeneous equation where the right-hand side is the 0 vector. We're trying to show that all the coefficients are 0. That can be done as in linear algebra with row operations. You can put these vectors in the columns of a matrix. And if you like, add a 4th column of all zeros representing the fact that I've got 3 zeros there. And then you do row operations. You're essentially trying to solve for C1, C2, and C3. And yes, most likely you will get just the trivial solution. So I'm trying to get it into reduced row echelon form. I'm trying to get zeros underneath this leading 1. So I try to get a 0 right there by multiplying row 1 by -1 and adding it to row 3, putting the answer in row 3. -1 times 1 is -1. Plus 1 is 0. -1 times 2 is -2. Plus 0 is -2. -1 times 1 is -1. Plus 4 is 3. Now I get a 1 right there by multiplying row 2 by -1. This notation here means add -1 times row 1 to row 3 and put the answer in row 3. But here I'm just going to multiply row 2 by -1 and put the answer in row 2, giving me a +1, then a -1, then a 0. I next want to get a 0 under this leading 1 in the second row, get a 0 right there. So now I'm going to multiply row 2 by 2, put the answer in row 3 after adding it to row 3. The first 2 rows are going to stay the same. I'll get a 0 right there. 1 times 2 is 2, plus -2 is 0. -1 times 2 is -2, plus 3 is +1. Now I've got leading 1s in every row. Now I want to get zeros above those. And the fact that I have leading 1s in all the rows means I will be able to get zeros above them, and I will ultimately, in the end up with a matrix that looks like this, without showing the details. And that implies C1 equals 0, C2 equals 0, and C3 equals 0. So I only have the trivial solution. That means this is a linearly independent set. Is it a basis for 3-dimensional space? It's a linearly independent set. Is it a basis? Does it also span R3? I hope it makes intuitive sense that it would. And that is the answer. Does anybody remember from linear algebra a theorem name that would say that 3 vectors that are linearly independent in R3 will also span R3? They'll be a basis. It's actually a couple different theorems that can be used. One of them has the word basis in it. It's called the Basis Theorem. 3 linearly independent vectors in a 3-dimensional vector space. R3 is a 3-dimensional vector space. Although, as we're learning here in our abstract algebra book, chapter 19, that's not quite a complete statement to say it's a 3-dimensional vector space. You should say it over a certain field. But in linear algebra, that field is almost always R. Yeah, it's a three-dimensional vector space over the field of real numbers. You could write dimension of R3 equals 3. If you want to emphasize the field, you could also put that as a subscript here. Dimension of R3 with respect to R over R is 3. Three linearly independent vectors in a three-dimensional vector space will automatically be a basis. They'll automatically span R3. That's the basis theorem. Basis theorem from linear algebra, which is not in our textbook. So would I require you to know it? Probably not. If I had you need it on an exam problem, I'd probably remind you what it is. When we're not modding by 3. It's not modular arithmetic. The coefficients, the components of the vectors are real numbers, and you're adding them in the usual way. This also could be proved with the invertible matrix theorem. Essentially, this matrix right here, whose columns are the vectors, is invertible. And actually, this calculation does confirm the same thing, that it's invertible. You could also calculate its determinant. See, it's got a non-zero determinant. That would be enough to say these vectors are linearly independent. And therefore, again, by the basis theorem, they span R3, they're a basis of R3. Okay, just a little reminder of some things from linear algebra. And yeah, I mean, technically it's something you should be able to do for the exam. I'd remind you of this kind of thing if I did put it on the exam. On the calculator, if you're in matrix mode, you can go to edit to edit your matrix. So I put the augmented matrix in as a 3x4 where the last column was all zeros. And then you can do math. RREF stands for reduced row echelon form, and then put the name, oops, not there, not in that menu. Reduced row echelon form of matrix. The matrix was called A. There we go. All right. Today, however, the main thing we want to do is start working through some problems in chapter 20. If you haven't done the reading, this is going to sound really scary. Well, maybe it'll sound scary even if you have done the reading. I do find the reading of chapter 20 to be probably the hardest reading so far in the entire book, personally. Extension fields. It doesn't start out too bad, but then it gets pretty hard by the time you get to about the third page on splitting fields. Yeah, I remember in grad school, splitting fields were kind of, for me, they were kind of my Waterloo. Like Napoleon met his Waterloo met my match. And this was the thing that I really was stuck on with my grad school preliminary exams. And I just couldn't understand how to do splitting field problems until I came and asked Eric Gossett for help. And he's like, well, why don't you do some calculations like with synthetic division and stuff? And I'm like, oh, that works. Because I was focused on just memorizing definitions and theorems like you find in this section. But the definitions and theorems statements, if you memorize them, they don't seem super helpful. They're hard to understand, and they also just don't seem super helpful. But what is helpful is doing examples and doing calculations. So let's start working through the exercises. Okay, you're going to want to try your best to work through these on your own as well. In chapter 20, just to get our minds around, well, initially here, the concept of a splitting field and what this kind of notation means that you see here. Let's go ahead and start with number 1. Describe the elements of Q of cube root of 5. Describe Q of cube root of 5. Well, the first thing you have to understand is, what does this notation mean? Okay, so that goes back to the definition of a splitting field and the paragraph right above it, in fact. Let F be a field. Let A1 through AN be elements of some extension field E of F. You start picturing it. These pictures are only so helpful. They're only a little bit helpful. All this reminds you of is that E is an extension field of F. In other words, F is a subfield of E. These A's, A1 through AN, are in E. Are they not in F? Well, they could be in F, though it's more interesting when they're not. Maybe A1 is right here, A2 is right here. I'll go ahead and put A3 inside F. A4 is over here, etc. They actually could all be inside F. Oops, sorry, you can't see that. Here's what I was drawing. They actually could be inside of F, but it's more interesting when they're in E but not in F. That's just more interesting. Or you might say it's harder. Coming back here, we use this notation, F of A1, A2 through AN, to denote the smallest subfield of E that contains F and those N elements. Smallest subfield of E that contains both the original field F and these N elements, some or all of which may be in F or may not be in F. It's an exercise, and you can take it to be equivalent to the fact that you can also say this is the intersection of all subfields of E that contain F and this set. Makes sense. Intersections make things smaller. So maybe something like this might be your picture for F of A1, A2, etc. Oops, starting again. Something like that. That's what the notation means. Hard to get your mind around that. It also leads into the definition of a splitting field. Let E be an extension field of F. Let F of X have coefficients in F and have degree at least 1, so it's not a constant polynomial. We say F of X splits in E if you can factor it like this, where the A1 through AN are in E and the coefficient in front, A itself, is in F. And E is, in fact, a splitting field for f of x over f if, in fact, E is this smallest subfield of some other extension field, I guess, containing not only f, but all these a's. Now, like I emphasized on Monday, the first thing to realize is that this does not mean E equals F union with just the n elements A1 through an. It does not mean that. If you only took F union with those elements, that would no longer be a field even. It's much bigger than that. So this field right here is supposed to contain all the rationals. It is supposed to contain the cube root of 5, but it contains more than that. It contains, for example, 2 times the cube root of 5, or 3 times the cube root of 5, or the cube root of 5 squared, which would be 5 to the 2/3 power. Because it is a field, and if it contains cube root of 5, it's going to contain 2 times the cube root of 5, 3 times the cube root of 5, cube root of 5 squared. It is going to contain infinitely more elements besides just the rationals and cube root of 5. How do we describe it beyond that, though? What does the directions mean here? Describe. Well, here's where we use some theorems in the chapter. Perhaps one of the more useful ones is this one, theorem 20.3. Let f be a field, and suppose you've got an irreducible polynomial over f. And if a is a 0 of that polynomial in some extension E of f, then f of a, meaning the smallest subfield of E containing both f and a, is isomorphic to this factor ring, which would be a field, because P of x is irreducible. Furthermore, and this is the more useful part, if the degree of the irreducible polynomial is n, then every element of this field here can be uniquely expressed as a linear combination. Linear combination of powers of A, where these coefficients are from F. So if we think about trying to apply this theorem to this example here, the A is the cube root of 5. I've got to find an irreducible polynomial, P of x, one of whose roots is cube root of 5. That's actually fairly easy. And according to this, I'd be able to write every element of this in this form, once I know what n is, where the c's would be rational numbers. What should I use for P of x? A polynomial with rational coefficients that's irreducible and also has cube root of 5 as a root. How about x cubed minus 5? That certainly has cube root of 5 as a root. Is it irreducible over q? Yeah, Eisenstein's criterion can come to the rescue. That's one example of something you can use. Back in chapter 17. We got a polynomial with coefficients in z. Yes, R1 has coefficients in z. If there's a prime p that does not divide the leading coefficient, does divide all the other coefficients, but whose square does not divide the last one, then it's irreducible over q. The leading coefficient here is 1. The x squared and x coefficients are both 0. The constant coefficient is -5. The prime 5 will satisfy Eisenstein's criterion. It does not divide 1. It does divide 0. It also divides 5 or -5, but its square, 25, does not divide -5. This is irreducible over Q by Eisenstein's criterion. With the prime taken to be 5. This P does not equal this P, right? That's a prime, that's a polynomial. So it's now in the situation in that theorem from chapter 20. With n equals 3, right? Degree of P of X is 3. Therefore, by theorem 20.3, we can describe Q of Q root of 5 as the set of all linear combinations of powers of A, this is the A here, up through the n minus first power. N is 3, so that's going to be up through the second power. And the first power, and a constant term, really meaning a linear combination where one of the basis vectors is 1. You can write this as, say, C2 cube root of 5 squared plus C1 times cube root of 5 plus C0 times, if you want an extra emphasis, you can put a 1 in there like that. 1, where C0, C1, C2 are all rational numbers. They are in Q. That's a C0, comma, C1, comma, C2, if you can't quite tell, but the 1 and the comma are kind of hard to look at here. C0, comma, C1, comma, C2. They're all rational numbers. Another way to write this would be to use power notation. C2 times 5 to the 2/3 plus C1 times 5 to the 1/3 plus C0 times 1. And since the last one is times 1, you wouldn't have to write the times 1. That's how you could describe this set in a way that would allow you to see what elements it has, and therefore do computations if you needed to. And it is a field. It is a field. It's not so obvious it's a field, I don't think. I mean, I'm looking at this and for example, I'm wondering, how do you get 5 to the negative 1/3 out of this? You must be able to, because it's a field, so the multiplicative inverse of 5 to the positive 1/3 is 5 to the negative 1/3. That should be in the field. But it's not so clear how to pick C2, C1, and C0 to make that happen. Would it be difficult? Should I try it? I'm not sure how difficult it's going to be. Let me just go ahead and experiment. I may fail. Okay. I'm wondering, how do you choose C2, C1, and C0 so that a rational number, so that 5 to the negative 1/3 is a linear combination like this? I never thought about that question before. So I'm thinking about it for the first time, and I have no idea how hard it is. So if I was going to try to solve this for C2, C1, and C0, I guess maybe I'd multiply both sides by 5 to the 1/3. That might be a good idea. That would be equivalent to 1 equals 5C2 plus 5 to the 2/3 C1 plus 5 to the 1/3 C0. Oh, but is that really that much easier? Doesn't look so easy still. I do know 5 to the negative 1/3 does equal 1 over 5 to the 1/3. And I could multiply the top and the bottom of this by 5 to the 2/3, and that's multiplying by 1, so it's not changing it. That'll give me 5 to the 2/3 over 5. Oh, hey, there we go. 1/5 times 5 to the 2/3. In other words, take C2 to be 1/5, C1 to be 0, and C0 to be 0. That works. So this was not necessarily helpful here. But doing this calculation, which is valid, every step here is valid. I realize 5 to the negative 1/3 is 1/5 times 5 to the 2/3. So this equation is true again when C2 is 1/5, C1 is 0, C0 is 0. It's of course not a complete proof that this is a field, but it helps make it more believable. What about 5 to the negative 2/3? 5 to the negative 1/3. What about 5 to the negative 2/3? That'll be 1 over 5 to the positive 2/3. Multiply the top and the bottom by 5 to the 1/3. Get 5 to the 1/3 over 5, or in other words, 1/5 times 5 to the 1/3. Those are equal. Oh, kind of fun. Kind of. Oh, and look at this. I could add these things and it would still be in there. 5 to the negative 1/3 plus 5 to the negative 2/3 would be 1/5 times 5 to the 2/3 plus 1/5 times 5 to the 1/3. There's how you could write this element of the field as a linear combination of these basis elements. The set of 3 elements, 1, 5 to the 1/3, 5 to the 2/3, forms a basis. For what? For Q of cube root of 5 over, what field is it over? It's over the base field, so to speak. It's over Q. I.e., the dimension of the vector space if you want to think of it as a vector space, cube root of 5 over Q is 3. This thing, Q of cube root of 5, is both a field and a vector space. And that's not a contradiction to say it's both, if that's confusing. It's a field. We can add and multiply things in the field, and it's still in the field. We can find inverses of elements. But it's also a vector space over Q, because I can write every element. Well, first of all, I can add elements in it. I can also write every element as a linear combination of these 3 things, where these coefficients are rational. So it's over the rationals. By definition then, or by that theorem, this would imply that this set of three numbers spans the vector space. Is it also linearly independent? That would take extra proof, but I won't do it. All right, that's the first problem essentially. We've done a pretty thorough job with that. The answer is essentially this, by the way. That's essentially the answer to describing, with some reasons. Let's move on to number 2. Two says, show that Q of, there's two elements there, square root of 2 and square root of 3 equals Q of square root of 2 plus square root of 3. That's just one element that has been adjoined. So, by the way, sometimes people use the word adjoin here. This is Q adjoined root 2 plus root 3. Don't misinterpret that, though. That doesn't mean Q just union with that one number. There's plenty of other numbers. Infinitely many others. The word adjoin is sometimes used, though. Here I'm adjoining both root 2 and root 3. But again, it's more than just that. There's infinitely many other things that are being adjoined as well. Thinking of the real numbers, for example, as being a bigger extension field we're thinking about, you can describe this as being the smallest subfield of the real numbers containing both the rationals and square root of 2 and square root of 3. And you can think of this one as being the smallest subfield of the reals containing the rational numbers and square root of 2 plus square root of 3. And the claim is these are equal. They're the same field. We show equality of two sets. We can show this is a subset of that and vice versa. This is a subset of that. One of those inclusions is easy, but it's not clear without some experience which one of those is the easier one. The easier inclusion is based on the fact that this is a field. This is a field containing both square root of 2 and square root of 3. So it also contains their sum, square root of 2 plus square root of 3, by closure, under addition. But wait a minute. This symbol represents the smallest subfield of the real numbers, for example, or the complex numbers for that matter, containing the rational numbers and the square root of 2 plus the square root of 3. But here's a field that does contain square root of 2 plus square root of 3. This one's the smallest. Therefore, this one's got to be a subset of that one. Let's write that out. But this thing is the smallest subfield of, for example, the real numbers, but I could pick the complex numbers. Containing all of Q as well as square root of 2 plus square root of 3. But I just said this field contains square root of 2 plus square root of 3 and the rationals. Therefore, this one being the smallest, therefore, q of root 2 plus root 3 is a subset of q of root 2 comma root 3. That's the easy inclusion. Though its argument is still tricky. You got to really think when you're concluding this. This is the way you want to think about it. You want to describe it. We know this thing contains the rationals. We also know it contains root 2 and root 3. Therefore, by closure and addition, it contains root 2 plus root 3. We know by definition that this one contains q and also root 2 plus root 3. And in fact, it's the smallest subfield of the reals that contains those. Being the smallest one means it's got to be a subset of the other one that contains them. Contains root 2 plus root 3. That is the argument. It's in the big scheme of things, it's an easy argument, but it seems tricky at first. The harder inclusion is the other one. So this thing is a subset of that thing. Maybe I should show, to do that, maybe I should show root 2 and root 3 individually are in here. Then this thing being the smallest subfield of the reals containing the rationals and root 2 and root 3 would be a subset of that one. Maybe it's the same overall argument. But how do you show root 2 and root 3 are in here? That's the hard part. And these are the kind of problems I've done in the past, but I always, if I haven't taught the course in a while, I'd always forget how to do it. And I was thinking about this for the first time again last night. Like, what in the world? How am I going to show root 2 and root 3 are in here? And what it took for me to figure it out is just some experimentation, some calculations. I know that root 2 plus root 3 is in here. And this is a field. These things are all fields by definition. Therefore, good things often happen when you take reciprocals. Therefore, 1 over root 2 plus root 3 would be in that field, the multiplicative inverse. Since it's closed under inverses. Okay, so what? Try to see if you can rewrite 1 over root 2 plus root 3 in some other way, perhaps. What other way? A common trick to try is to try to rationalize the denominator by multiplying by its so-called conjugate. And if I do it to the bottom, I got to do it to the top. The trick here is that's going to get rid of the radicals in the bottom. Of course, you'll have radicals in the top. If you FOIL out the bottom, root 2 times root 2 is 2. The outside and inside terms cancel, and last times last is minus 3. And hey, that's a negative 1 there. So this simplifies to root 3 minus root 2. Okay. Is that helpful? Not so clear that it's helpful. Trying to remember what I did last night. Okay, so the root 3 minus root 2 is going to be in there. How about its reciprocal? Maybe I should try to figure out its reciprocal as well. Do the same kind of trick. Look good? I think there's no mistakes. Follow the logic here with me. 1 over root 2 plus root 3 is going to be in this field because it is a field containing root 2 plus root 3, so its reciprocal will be in there. What does that reciprocal equal? It equals that. So this is in there. And therefore, its reciprocal will also be in the field, and it equals this. And what happens if I add these two equations? The equality between those two things and these two things. The root 2's are going to cancel. Leaving me 2 root 3 when I add them. In other words, root 3 is 1/2 times this thing. Weird equations, but true. And that's enough to say then that root 3 must be in this field. Why? It's the logic the whole way here. Root 2 plus root 3 is in the field. Therefore, its reciprocal is in the field. Therefore, this is in the field. Therefore, its reciprocal is in the field, and it equals this. Field is closed under addition. If I add these two things, it's also in the field. 2 root 3 is in the field. If I divide by 2, if I multiply by 1/2, it's still in the field because 1/2 is in the field as well. Closure, 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 closure. A bunch of closures is what I'm doing here. I added these equations to get rid of the root 2. I could have subtracted them to get rid of the root 3. Also, I could have said, let's say this one minus this one. 1 over root 3 minus root 2 minus 1 over root 2 plus root 3 would equal 2 root 2 if you take, I just took this equality and subtracted this one. And so root 2 is 1/2 times that thing. That's also in there. Oh. And that does it. That's what I wanted to do. I wanted to show root 3 and root 2 were in there. And therefore, since this is the smallest subfield of R containing the rationals and root 2 and root 3, it must be a subset of that. Done. Therefore, Q root 2 comma root 3 is a subset and a subfield of Q of root 2 plus root 3, and therefore, since I also proved the other inclusion, they must be equal. Therefore, that's the case. Okay, that's a pretty long, tricky argument that involves doing calculations that you wouldn't necessarily you would do ahead of time. Could this show up on the exam? Probably not without some help. But it's still worth thinking about, if for no other reason than to understand the reading better and the lectures better. These examples are what's going to help most. Let's not go on to the next example. Let's just continue thinking about this some more. Q adjoin root 2 comma root 3. It does turn out can also be thought of as Q adjoin root 2 adjoin root 3. That's also a valid way to think of it. It's an iterative process here. In other words, first adjoin root 2. And then to that adjoin root 3. X squared minus 2 is irreducible over Q. And x squared minus 3, well, it's also reducible over Q, but you can say more. It's irreducible over Q adjoin root 2. Though I haven't really proved that. So according to the theorem we were looking at, every element of f of a can be written in this form. I should be able to say, based on that, that this initially can be thought of as the set of all C1 times root 3 plus C0 times 1, as C0 and C1 vary over Q root 2. In other words, i.e., the dimension of the vector space Q root 2, adjoin root 2, then adjoin root 3 over Q root 2 is 2. Your two basis elements are root 3 and 1. But wait a minute, the C's are from Q of root 2. So like I could replace C1 maybe with, let's avoid subscripts now. C1 maybe with A plus B root 2. And C0 maybe with C plus D root 2. As A, B, C, and D vary over Q. And if you expand this out, you can write this as A root 3 plus B root 6 plus C plus D root 2 and evidently these elements root 3, root 6, 1, and root 2 are going to be basis elements. So this is a vector space over Q. Yes, they will, i.e., the dimension ultimately of this thing over Q is 4. Not really proving things here, but does it make intuitive sense? Just using that theorem. Sometimes this is visualized in what's called a tower of fields. We can put Q down here, Q adjoin root 2 here, and then ultimately Q adjoin root 2 and root 3. And then you put numbers next to these lines representing the dimension of the higher field as a vector space over the lower field immediately below it. Q root 2 comma root 3 is a two-dimensional vector space over Q root 2. That's essentially what this says here. This is also two-dimensional, though I didn't write out this one here. But ultimately, it's four-dimensional right there. Now, since this equaled from the previous page, Q root 2 plus root 3, that must also be a four-dimensional vector space over Q. So it must be the root of an irreducible polynomial of degree 4. What polynomial would that be? Root 2 plus root 3. It must be the root of an irreducible polynomial over Q of degree 4. Because it's the same as this, and we just found that this is a four-dimensional vector space over Q. That takes some experimentation as well. And here's the experimentation I was doing last night with this. I was like wondering, first of all, what would happen if I square this thing? I'm trying to find a degree 4 polynomial that this is a root to. Foil it out, I get 2 plus 2 root 6 plus 3 is 5 plus 2 root 6. Foiled. And then if I subtract 5 from both sides, I could say root 2 plus root 3 squared minus 5 equals 2 root 6. And then I could get rid of that root 6 by squaring both sides. If I square that, I'll get 4 times 6, 24. And then I can multiply this out. Root 2 plus root 3 to the 4th power minus, it would be 10 root 2 plus root 3 squared plus 25 equals 24. And then I can write root 2 plus root 3 to the 4th minus 10 times root 2 plus root 3 squared. Subtract 24 from both sides, plus 1 equals 0. Hey, it looks like root 2 plus root 3 is a root of p of x equals x to the 4th minus 10x squared plus 1. The only question is that an irreducible polynomial over Q? If it is, then that does it. That's another way to realize that this is a four-dimensional vector space over Q. That this is here. It's not so easy to prove this is irreducible by the looks of it. Eisenstein's criterion is not going to work. Try a mod P irreducibility test for some P, but it's not clear that that'll work. To try it and see it. You know, sometimes the mod P irreducibility test never applies. Doesn't mean it's wrong. It just means it does not apply to the problem. I didn't take the time to try to figure it out. But I did take the time to have Mathematica find the roots of these things, of this polynomial here. That's what we'll end class with today here. Solve x to the 4th minus 10x squared plus 1 equals 0 for x. Gives the answers in those forms. And square root of 2 plus square root of 3 is in fact one of those. It's the one that's close to pi, 3.14626. definitely not equal to pi. Okay, it's only close to pi. Okay, so that was the extent of my experimentation with this last name. So this is not an easy subject, but the examples are easier than the theorems and their proofs themselves. Make sure you study the book's examples. Make sure you work as much as you can on the practice problems. Okay? Have a good day.